Number E.
In this set of notes, we're going to talk about the number E. The number E is a really important number in mathematics, such like pi is a really important number that we use in geometry. And like pi, E is going to be this number that has an infinitely long decimal that goes along with it. You may recall that pi is 3.141598979323383279502888. What comes after 88? 4197 and so on, right? Anyhow, E is going to be a number that looks a lot like that. I mean, it's a different one, but it has a decimal that goes on forever. And what we're going to do in the notes here is we're going to investigate at the beginning what that number is. Then in the second part, we're going to look at how we can create applications with that number. So up at the top here, you've got this thing you may or may not have ever seen. Occasionally in my classes, I might mention it, but I don't get into a lot of depth on like how to read it. But the way that this is read is like this. The limit of a function f of x as x approaches infinity. So you have a function that's called f of x. In this case, we don't know what it is, but it would be anything that you can plug an x value into it. And what we're interested in doing is plugging in very, very large values of x. In fact, we want to plug in the largest possible thing that we could for the x and then investigate what does this function start to do as it produces outputs. Do you continue to get larger answers? Do you continue to get smaller answers? Does it happen to settle off like you might imagine a horizontal asymptote? But that's our interest here, is to see what happens to a function when you continue to put in very, very large numbers. Okay, this is the function that we're going to investigate at the beginning of our notes here. Our function is going to be 1 plus 1 over n raised to the n power. So the n's are basically your x's, right? And you can even see that here. It says n to infinity instead of x to infinity. So n is our x, and we're going to continue to plug in very, very large numbers and larger numbers into those spots. But the reason that we're going to use an n here is because it might remind you of something that we did in the last item, which was compound interest, where n would be the number of times that you compound. Difference with this versus what you did see there is we don't have an r value. We just have like a 1 in that spot, and you also don't have a t value that would be in there. But those things are going to get addressed a little bit later, and you're going to see how this does come back to interest rates. For now, we'll just investigate this as it is with the single variable n. So I have a table of values that I want you to complete. And I'm going to ask that you complete that before I give you any more information, before you go further into the video. Okay, so here's your expression. We're going to first evaluate it for 10 to the first power. 10 to the first power is really just 10. That's all I'm asking you to do, is to plug a 10 into both of these spots, run that calculation, then write down a number. Whatever answer you get, go ahead and round it to, let's do 4 decimals. I think that would be a safe bet here. So do 4 decimals. When you're done with that one, you're going to evaluate for 10 to the second power. In other words, 100. Okay, so we're jumping to a larger value of n or x. We're going to use a 100, plug that in, same thing, round it off to about, I think I said 4 decimals. So round it off to 4. You're then going to go and do the same thing for 1,000, then for 10,000, 100,000, and then for a million, maybe at this point. All right, here's the table completed. Hopefully you took the opportunity to try this out and you got these numbers as well. As we look at the numbers, moving down the list here, at the very beginning, it really doesn't look like much at all. You just get the 2.59, and then after that, you get a 2.7. So it really doesn't seem like anything special is happening there. But as the value of n increases, and we're increasing by a factor of 10 every time, as that increases, you actually start to see the numbers settle off. Right at the beginning, you got, which is really about 2.6, then it moves into the 2.7, and it seems to get locked in at that number. But then you start looking at the other decimals, and it now begins to get closer to 0.718. At the end here, I did round it up to a 3. It's actually like a 2, then an 8. but I had suggested that we round to the nearest 4 decimals, so technically it does round up. Here's what it looks like in the calculator at the end part there, so it's not really a 3, just to be aware of that. That's a rounding kind of thing there. Oh, in addition, TI calculators, they have a cool feature that you may or may not know is available, and it doesn't really matter what version of the calculators you have. Like at some location on the calculator, you can do this. What I did to calculate all these is I went to y equals, and I typed in the function. So then I had that saved back at the home screen. What you could do, at least on this calculator here, I can type alpha trace, and it allows me to choose a function that I had in the calculator. Then using function notation, which is, what we're talking about here anyway, you can ask it to evaluate for whatever numbers. So if I want the 10, I just type in 10, and you should close the parentheses, though it's not technically necessary, and it evaluates that function for you at that number. So this was a way that I could just quickly run through and grab all the numbers that would be on there. All right, so as you evaluate this for larger and larger values, and you can continue on, you're going to start to see that it settles off at a certain number, sort of like the idea of an asymptote that we studied in rational functions. All right, so here it says, as n increases, this expression appears to get closer and closer to the number 2.718. I'm just going to round it off there because I know that the 3 is a bit of an issue rounding up. Swiss mathematician Leonhard Euler, that's pronounced as Euler actually, Leonhard Euler, proved this, and the limit is called E in his honor. All right, in addition to that, the function e to the x power, so our exponentials here, e to the x power is called the natural exponential function. The reason that the word natural shows up here is that this number that he discovered actually shows up in nature. It shows up in natural things in the world, and it's a bizarre sort of thing. And if you want to research, just out of curiosity, check out that number e and notice like all the things that it just naturally shows up in. All right, this is so important in mathematics that on a calculator, almost any type of calculator is going to be on the main keypad. You don't have to go and search for it. All right, mine is going to be a little bit difficult to see, but there's a button on my calculator that's got an LN on it. And if you press shift, that button, I doubt you can see this. If you can, great. But right above that is e to the x. And on some calculators, you'll have e to the x and then you shift to get the LN button. But it's always like right up there because it's so important. In this next part, I'm going to show you something that is very, very difficult. It's going to be hard to understand, but what I'm going to ask is that you're open-minded as I go through it and try and take as much as you can from it. In the end, what this is going to do is help develop a formula that you're going to apply to other problems. So you're not going to have to reproduce this. You're just going to have to be able to use the formula later that's shown to you. Okay, so be open-minded about it and just see what you can take from it, okay? The setup for this is something called continuous compound interest. When we looked at compound interest in the other activity, there was a discussion about wanting to be able to compound the interest as many times as we can in a year because you're able to go to the bank as many times as you want, right? So compounding quarterly is nice because that's 4 times a year, and then monthly is better because it's 12 times, and daily is 365 times. But we should be able to compound it every minute, every second, every fraction of a second. An infinite number of times is what we should be able to do. So that's what continuous compound interest is going to be, is the idea that it is compounding every moment, right? So we don't ever have any of these awkward breaks in time with that. So let's take a look at this. What I have right here is your compound interest expression, except without a t-value, because the t-value is really easy to work in later, and I can explain that part once we get to it. But the rate is kind of an important thing here. It's going to be embedded inside of it, so I can't come back to that one later like I can the t. The k value To be honest, I don't know why I chose k value for this. It's the same thing as the n value, and it might have been less confusing if I just stuck with the n, but I happen to type this as a k. Okay, so this is our compound interest expression formula. And what we're going to look at is the k value going to infinity. So not doing quarterly where k would be 4 or monthly where k is 12, but when k becomes this infinite number. Okay, and the next few things I'm going to show you is just some math. And at the moment, you don't know why I'm doing it, and I don't want to get into why I'm doing the actual steps. I just want to show you that these steps are algebraically true. And then at the end, there's a neat little response from it. My first step is going to be changing this fraction to look like this complex fraction. To me, it's difficult to think how I go from here to that part, so I'm going to try and explain why it's the same thing by imagining going backwards to here. So in the complex fraction here, I have a 1 over the fraction k over r. To divide two fractions or a whole number by a fraction, to divide, you can use a rule that's called keep, change, flipped. And what that would be is taking the 1 and not dividing it by the fraction, but taking the 1 and multiplying it by the reciprocal of the denominator. So if I take 1 and multiply it by r over k, I get back the r over k. So I hope that that justifies that these two things are, in fact, still the same. The next part is going to be making this exponent look the same as that denominator, sort of like what I have here, right? So I want them to look the same. I'm not going to change what's on the bottom. What I want to do is actually change the top. So I'm going to take that k and I'm just going to put it over r. I'm just going to do that. Okay, and now they match. But you can't just change anything you want to without some sort of a balancing to make it still true. Okay, so the way that we make it true is we throw everything into brackets or parentheses and then raise that to an r power. Essentially, these r's actually just cancel out each other and we're back to having our k value. So the way that works is called the power rule, that if you have an exponent raised to another exponent, you actually just multiply them, right? So if I multiply k over r by r, the r's just cancel out and I'm back to k. So if I want to place the k over r, just make sure that I have that other exponent hanging out on the outside and everything is fine. Okay, so what was the point in making this look like that, which I think your opinion would be is that this is worse, right? It's larger and it's got all these fractions there, but what's the point of doing it? The point is that if you look just inside the brackets, right? Don't worry about the r that's out there. If you look just inside the brackets, this is the same thing as that, and I already mentioned that was a goal. They're the same thing, and I've also got this 1 plus 1 over that item. And if we go back to the beginning of the notes, that's this guy. The only difference is that instead of having an n, I've got a k over r, right? And r is a constant, it's just a rate, so don't worry about the r value. If I evaluate this as k goes to infinity, then I might as well be evaluating this as n goes to infinity. And when I evaluate this as n goes to infinity, I get, where are you? I get e. So, here's the craziness of it. All the stuff in the brackets, if I take k to infinity, then all of that just simplifies down to the number e, the 2.718. But I still have that little r that's just hanging out at the end. So all of this, when k goes to infinity, when I want to compound continuously, it all filters down to just e to the rate. The rate is the power. Okay. So let's take this idea and start to develop it into a formula for continuous compound interest. It can be said e to the r is the factor applied to the principal. If I go back to this part here, you could imagine the principal just sitting out front, the p-value just sitting right out front of that, and then all of that is actually e to the r. So it can be said that e to the r is the factor applied to the principal. If raised to the respective time t, the current value can be found. So p of t, this will be our balance at the end of some amount of time t, is going to be your principal multiplied by e to the r, but then that has to get raised to whatever time you want. And that goes all the way back to like our hamburger problem in any exponential growth, that you have some factor raised to a power. That'd be there. Okay, but here's the neat thing with it too, is this is also the power rule, which I had talked about up there, that if you have e to the r power and then you raise it to the t power, let's give a little example over here to the side. If you have x cubed to the second power, that's the same thing as x to the sixth power. It's called the power rule. You get to multiply exponents when it's an exponent to an exponent. That's what we have here. We got r to the t power. So you can also write this as p times e to the rt power. So you don't need to have separate exponents. You can actually just put them side by side as a product. This is going to be our formula for continuous compound. So if you come across any problems, here's one here. If you come across any problems that mention compounding continuous, or they say continuous compound, that means you want to use this formula here. Example 1, we got $15,000 that's invested at 8% and it is compounded continuously. What will be the balance in 2 months? Okay, so we got a principal of $15,000 because it says continuously. That means you're going to multiply by e to the rt power. The r is going to be 0.08, put that in parentheses, is going to be 0.08 for the 8%. Okay, you don't have to change anything in that spot. The percent just goes in that spot like that. Then you're also going to have the time frame, which is usually some number of years. But for this, I figured I would go ahead and show you something a little bit different. If you did something by months, that's totally like fine. Just don't put a 2 here because it's supposed to be in years, so that would represent 2 years. So we just think about this, 2 months is the same thing as 1/6 of a year, right? 2 months is 1/6 of a year. So right here, we can just do 1/6. If you ever have anything in any terms of months, just put the number of months over 12 and that'll work. So even if you had something like 30 months, you could just do like 30 over 12. You don't really have to reduce if you don't want, but you could. Anyhow, this, yeah, that's it, man. That's the equation if you're going to do continuously compounded. Like visually, I think it's a lot shorter than the other type of compounding. Okay. You are going to need a calculator to run this one, though. No way around that. Okay, so I'm going to take the 15,000, and as mentioned previously, there should be a button on your calculator that allows you to type e to a power. On some calculators, you can just type the e. There's a button for e somewhere. You never actually have to type in the 2.718. There's no calculators that you would need to do that. Not any calculators that can do exponents as well, I guess I should say. Anyhow, we'll take e, we'll raise it to the 0.8 times, I'll do this in parentheses just to make it look a little bit better, 1/6. All right. Overall, it doesn't look that pretty anyway. I probably could have done parentheses around the 0.08, so I didn't have that, but it's still going to work. That's what we get, which is going to be $15,201 and about 34 cents. Always assess your answers when you're done with things. Does it seem reasonable? Yeah. 15,200 means you've gained $200 since then, so it's not too far of a jump from there. It did happen over 2 months, which is a pretty big leap as well, but 8% also happens to be a somewhat large percentage change, so